So let me first give you a panorama of the signatures you can find in the wild, and I will just include signatures which were proposed at the first call of the NIST, and in particular the ones that were at least selected up to round 2. In the following, I will draw big bubbles, which area is proportional to the signature size. So I don't care right now of the public key size, of the time, whatever, just think of the SIG size. So on the one hand, like the 3 first bubble, like the pretty big ones, are the hash-based ones, so Picnic, Sphinx, and XMSS. Okay, so that's pretty cool. And then we have the 2 structured lattice ones, so now standardized, sorry, Dilithium and Falcon. And as just a reference point, the classical ones, okay, it's not NIST, but it's, I mean, some of them are NIST standard, RSA and ECDSA with Edward curves. As you can see, there is a huge discrepancies in terms of sizes. And what I'm gonna present today fits roughly between Falcon and Dilithium. And there is a cute squirrel. Okay. So it's smallish, at least compared to other NIST candidates or like post-quantum ones, it's quite small. But also, and most and foremost, it's unstructured. And that's why we designed this scheme. It was to answer the NIST call on unstructured signatures. So I'm speaking of lattices, structured lattices, unstructured lattices. So let me just give you, maybe, probably you don't know, you all know about lattices, but let me just give you 2 points that you need to remember on lattices. So you take the Euclidean plane, Euclidean space we're living in, and you take a bunch of points which are very regularly spaced. So you have a very nice grid structure. You will have something a bit more powerful. You want that the sum and differences of vectors remains in your set. This gives you this beautiful picture. Nice, so lattice, okay. And as a linear algebra object, we will represent it using vectors, and in particular bases. So you can take 2 vectors which are linearly independent here, and you will represent a full lattice with that because you can obtain all points by linear combination of them, integral linear combination. And not all bases are actually born equal because, as you can see, you can take like the plane one, and they are way smaller. Okay, and much more orthogonal. So let's call that a good basis and the other one a bad basis. So first thing you need to remember about lattices is that if I want to find a short vector in an arbitrary lattice in high dimensions, this should be a hard problem. Okay, Aitai stated that in 98. That's foundation of why we're using lattices in crypto. Second thing is that if you have a problem, whatever it is, like for instance, CVP, SVP, whatever else, Gaussian sampling, you want to use a good basis because your problem becomes easier and easier with a better basis. So this is like a motto that every lattice cryptographer has used since basically 2000-ish. That's the only thing you need to know about lattices for the rest of this talk. So now still on the recap, let me just give you a brief, is it still working? You can see the pointer, yes? Okay, cool, awesome. A bit on hash and sign. So you saw this morning there was like basically 2 categories of signatures: the hash and sign and the Fiat-Shamir transform one. Let me just give you a brief overview on how you construct hash and sign, which is basically like the lattice hash and sign over lattice, which will be the lattice version of RSA. Okay, so first of all, you take your favorite lattice. For me, it's the hexagonal lattice. It's like very round, it's nice, very symmetrical. And you will hash your message somewhere in between the point of your lattice. So here, my gold point M here. That's the hash of the message. Then you will sample a lattice point which is close to the center M. Okay, so let's say, for instance, I've selected this vector V here. It's inside the lattice, it's close enough, okay? And I'll take the difference between the two because it's short. And I will call that my signature, okay? Perfect, this is how we construct a signature in the paradigm. So now you want to verify, and the first thing you will verify is basically the dual of what I just said. You want to sample close enough, so you will check that you're close enough. Well, so first of all, you check that you're inside an acceptance radius, which states that you're small. And then you will have this functional equation to verify, which states that you want this difference here to belongs to the lattice. Okay, so this is easy to verify with a public key, which is like whichever basis you have, checking is just a matrix multiplication to check. And if these two conditions are verified, you accept. Okay, you want your signature to be secure. So what does that mean? First of all, you want it to be secure against forging, which means you should not be able to construct signature to a given message without knowing the secret key. Okay. So the verification I said was checking 2 points. One, that the candidate is inside the lattice. Second, that the candidate is close to a given center. So basically, if you just translate that into lattice jargon, it's just say that you're solving a closest vector problem instance. I give you an arbitrary point of the space, M, and I construct whatever lattice point which is close enough. Okay, so you need this problem to be difficult, because forging amounts to this. So if this is hard, it means that the Gaussian from which you were sampling, remember the previous slide, should be sharp. You want to have a point which is close. Okay, means that the Gaussian must have small variance. And if you remember my motto here, the better the basis, the easier my problem becomes. It means that to solve this sharp Gaussian sample, I need a good basis. So I need a good private basis. Okay, so I want a private basis with short vectors. Okay, that's a good point. Okay, now second thing, you need to be secure against key recovery. Key recovery amounts of starting from the public key and finding the secret key. And if you have that, of course, you're forging, you can do whatever. You're the king of the hill. So basically, okay, let's see. It amounts to lattice reduction. I'm starting from an arbitrary basis and I want to find a good basis. Here you have lattice reduction in dimension 2. So I was starting with a bad basis, and with some clever manipulation of the vector, I found the short vectors. This amounts to what is called lattice reduction in general. And so to have this problem difficult, you want 2 things. You want to be in large dimension, because as Aitai said, finding short vectors is hard, but I should add in high dimension. And you also want a bad public basis. Okay, this should be public, sorry. Bad public basis. Because if you start with public short vectors, you have nothing to do, you're already broken. So, okay. You want high dimension and bad public base. Okay, so now we can just move on to the rationale of constructing this hash and sign. You have 3 main ingredients: the keygen, the signing, and the verification, 3 polytime algorithms. The keygen will generate the private basis and the public basis. The signing will require some Gaussian sampler, which should be sharp, as I said. And you want the Gaussian sample to have a good private basis to sample sharply. Okay? And verification will require the knowledge of a public basis. Okay, that's it. That's the rationale. Now let's move to Squirrels and the choice we made in these boxes. Okay, nice. For the sampler, we chose to use this client sampler, which is the one which is used in the literature, in particular in GPV, which is where these hash and sign over lattices were first proved. Will mean that we need to have a very specific private basis with a good geometry with regards to this sampler. So I will explain a bit later what it means. And we want the verification to be fast. So the easiest linear algebra operation you could think of, the fastest, would be checking a single linear equation. Linear algebra amounts to computing linear equations. So the fastest one is computing a single one. Okay. And if you want to have this, you will need a bit more, and you will need to have special arithmetic properties for the basis. Okay. Then you need to adapt your keygen in order to have both good geometry and this special arithmetic property. Okay, so that's pretty cool. And all in all, you need to yield this public basis, which is made of bad vectors. And somehow a way to do that is to send the so-called Hermite form, which is a generic form over integer lattices, which consists in very long vectors. Okay. So this is basically the very simple design rationale of the scheme. Okay, so I tricked you a bit because I say, oh, it's easy, we have good geometry, good arithmetic properties. What does that mean in more precise terms? So we have 2 terms. Like, on the one hand, we have the good geometric structure, and we will have this good arithmetic structure. Let me start with the geometry. This client sampler, the quality, your ability to sample sharply, depends on the max of the Gram-Schmidt norms of your vector. So basically, if you remind your bachelor classes of linear algebra, if you have a bunch of vectors in the space, you can orthogonalize them, and taking the norms of this orthogonal vector gives you this. Okay. If you draw the norms, you will get something which usually looks like have a nice geometric decay because it's a log. Okay, so you have a nice profile of the basis, and if you want to have a very good sampling, you actually want something which is close to being flat. You want a flat profile, which means that you need a low decay of the Gram-Schmidt, so you need to construct the vectors one after another, and you will choose a region where you are choosing them with regards to what you already sampled. So you have like first vector, then you will sample something which is close to be orthogonal to them, so that you will have this very nice flat decay shape. Okay, we can do that. And then this good arithmetic structure, which is, okay, how do I check that I'm belonging to the lattice in only one single equation? So you can represent an integer lattice not with a basis, as I did, but with a co-representation, which is saying, oh, I'm the kernel of some map to the integer mod q. Okay. Then belonging to the lattice amounts to checking one matrix multiplication mod q. Okay. And then if m is equal to 1, then it means that it's only a single equation to verify. You only need to check this, that vector scalar fixed A mod q is equal to 0. Okay, this is exactly what we want. So these cocyclic lattice are actually almost everywhere. And generically, if you take a random lattice, you have a very random integral lattice, you have a very high chance of finding them, around 80%. You can compute that. And you can actually go beyond just hoping for 80%. You can enforce this by asking the determinant, for instance, to be square-free. Okay, let me give you a bit of a dimension 2 example. If you know my talks, I love doing dimension 2 examples because this is the only one I can draw. Okay, so how to construct a good basis? Okay, let's first sample a random vector in the space, not even in the lattice, of of dimension approximately what I would want. Okay. Then I will round this vector and say, oh, okay, this will be my first vector of the basis. Okay, too bad because it's outside my circle, so maybe it's a bit too long. Maybe it's bad, maybe I lost. Okay, I can do it again. Okay, new vector. I'm rounding it. Oh, nice, now it's inside the circle. So, okay, let's say that's my first vector. That's pretty cool. That's not a lattice. Right now I have the point 0 and the point I just sampled. Okay. It's a lattice though, so I can do sums and differences. So it means that everything which is a sum or a difference lies in my lattice in construction. So I have a line at the moment. Okay. But then I say, okay, there is this single linear equation to verify, which means actually that the value q, the determinant of the lattice, will be known in advance. It's a public information. So, okay, say in my example that q equals 7. Okay. Then I will draw the orthogonal line to the line I already have. Okay. And then I will intersect this line exactly where I need to have a determinant which is equal to 7, which means that there is only 2 points where if I draw the rectangle that goes by the first vector and this orthogonal line, this area will be 7. And actually, you can prove by a bit of linear algebra that the area of this rectangle will be exactly the area of the corresponding lattice that I will construct. So that's why we're constructing here. Okay. Then what I will do is construct all the points, which actually gives this orthogonalization. And it's very easy to do. I intersect this line with the set of integer points. So I have this bunch of points here. Then give you like 2 lines, and I will do exactly the same on the opposite point, because of course everything is stable by subtractions. Okay, so that's pretty cool. Okay, I remove all the construction effects. Okay, I have a bunch of points. And in this bunch of points, I actually have a basis. And this basis, I will use it to complete all the points in the space. And I have, oh, now a full lattice. That's pretty cool. And I have actually, by construction, a good geometry, because I chose a small first vector. The second vector was chosen optimally to have the right determinant. So it's actually the best basis I could find. And from that, I can construct the Hermite form of it. Longer vector, I didn't lie. I have a way longer, 2 longer vectors. And you can check that for this particular lattice, they will satisfy this equation. So vector xy belongs to the lattice if minus x plus 4y are equal to 0. That's sufficient to verify the belonging to a lattice. Okay, if you put all of that, okay, I cheated. I did dimension 2, but believe me, you can do it in dimension n. If I do that, you can instantiate the full scheme, which is basically GPV on steroids, and you get these concrete values. Okay, I just draw your attention on the signature size, which is actually very small. It's in between dilithium and Falcon. I don't draw your attention to this part, which is not very small, but I draw your attention again to the verification, which is actually on the same order of magnitude as Falcon and dilithium. Okay. Maybe with pictures it's a bit better. So as I told you, the signature size is literally in between Falcon and dilithium. Okay. And now the thing I said I would not draw attention to is actually the public key size, which is basically this. It's big. And actually there is a reason to that. So the NIST asked for unstructured lattices. And if you think unstructured, it means that the representation in terms of linear algebra, in terms of basis, must be unstructured. And unstructured means you can't compress. And if you can't compress and you have an n-dimensional object, it means that you need an n by n matrix, which means that you have a space complexity which is quadratic in the dimension. And this is what quadratic in the dimension actually means. So basically, answering the NIST call in terms of lattices means this. That's how it is. So all in all, this Squirrels proposal has good and bad points, like every other proposals. On the good points, we are unstructured. We're using plain lattice assumptions. So the security amounts to SIS and SVP on plain lattices. It's fast. The signature is actually small, competitive to Falcon dilithium. It's very tailorable. You can really choose the dimension, choose the modulus really, really precisely. You can close the gap between forging and key recovery. However, it has a huge public key. I can't do anything about it. The keygen is pretty heavy because, remember, you had to generate this huge public key, so there is a limit on what you can generate. And it actually uses floating points. This client sampler, if you want to implement it in a fast manner, it uses heavily floating points. It might or might not be a problem, depending on which device you are trying to implement your scheme. It's a bit the same problem as for Falcon. There are ways to circumvent that, but it's not easy, so I put it in a drawback. Natural instantiation of it would use floating points.